David, you're going to talk about ScalPL.
Yeah, ScalPL. ScalPL. I'm Dave. I'm going to talk about some work. ScalPL, it actually started years ago here at Oregon Graduate Institute. A guy named Robbie Babb was starting something called large grain data flow. He basically was taking data flow diagrams in software engineering, data flow diagrams, and saying, why can't these run in parallel processors just as is, rather than the weird ways that we're writing parallel programs these days. So he did a little bit of experimentation with that. I joined him as a grad student in about 1985 or something like that. And I took what he did and kind of said, we got to throw this out and add this, and so came up with large grain data flow 2. And then came up with a formal model for describing how it all could work in a parallel, in a very portable way on different kinds of parallel processors. And that work was called FNets. The formal model is called FNets. That was my PhD dissertation at Oregon Graduate Institute. And then from that formal model, which was just the very basic, easy part, I built a language called, at that time, software cabling, and you'll learn why I was using kind of hardware type ideas in the description. It has since been renamed ScalPL, or Scalable Planning Language. It's the same thing, just with different terminology. So this talk, I'm just going to talk about some of the basic principles for about half an hour, then, which means I may go a little bit long here. Then I'll very briefly talk about the arrays, which are kind of weird, classes, which are kind of weird, and then wrap up. There's another ScalPL out there. I don't think you'll confuse this with that. I think there's only been one paper ever written on it. I wrote a book on this one recently. It's all described here and all the reasons that it's designed the way it is and all that kind of stuff. The book actually talks about any kind of situation where you want to have lots of entities working together on the same problem at the same time, how to do those. My own motivation was in the parallel computing world. But before I wrote the book, I kind of noticed, look, people, even if you're talking about people working together or different offices or parts of the company working together, you're going to run into a lot of the same problems. So why don't we just generalize all of this into scalable planning in general? So when I talk today about a plan, I'm going to be talking about a program. But the book kind of generalizes a plan to any kind of a plan. That's the cover of the book, which I just held up. Okay, the goals of ScalPL, it's really tough to think about different entities working on the same problem at the same time for lots of reasons. I don't know how many people here have done parallel computing or stuff like that, so there's a couple of them. Figuring out what the different pieces should be, how they should interact, when they should interact or communicate. How do we keep track of all this stuff going on with our one-track minds where we're kind of like to stay focused on one thing at a time. And specifically, we'd like to have some kind of a way of representing our program that's portable across all kinds of computers with all kinds of different numbers of processors, scalable so that as we add processors, we can make use of more and more of them, efficient so it's not wasting time just trying to uphold the model of communication or whatever. Flexible. It would be really nice if we could use traditional languages and not lose all the tools and all the effort and education that we've had over the decades. We'd like to make use of as much of that as we can. Correctness, it'd be nice if it was verifiable, formal, etc. Be nice if it had, there have been papers and stuff written on structured parallel programming, and they all have kind of a different feel for what structured means, and I'll give you my feel for what that means. And if you can feed object-oriented principles and stuff in there, that's great too. How about fault tolerance? How about real-time constraints? This is made to kind of satisfy all that stuff. And to satisfy all that stuff, it meant going outside the bounds of what a lot of people think of as programming. And that's one reason that this has had some problems getting traction. And I'm just hoping that once people realize they really do want to achieve all these things, maybe they'll look in this direction for a solution. I won't cover all of these things today, but those are the kinds of things that it's meant to address. Traditional approaches to parallel programming, there's thread-based parallel programming where you break your process up into threads and you manage the threads, and they usually share data through shared memory, and that's usually run on uniprocessor or unicore, multi-core type platforms. Message passing, same kind of thing. You're manually breaking up the process into pieces and having them communicate, so you're managing all the data movement and all that kind of stuff. Both of those, the programmer's managing all kinds of stuff that it's a good question whether they should really have to manage, and they're not managing it necessarily to express the solution in the program. They're managing it to try to get it to work on some particular kind of parallel processor very efficiently. So it'd be nice if those kind of meshed more closely. Non-determinism is a fact of life in parallel programming sometimes. So in sequential programming, it's nice because it's all deterministic. If you have a program and with the same inputs, and here I'm counting as inputs not only arguments and inputs, but calls to the operating system, etc. If you take all those into account, it's going to produce the same answer if it gets the same inputs. With parallel programs, that's generally not the case, because things running on different processors, if they run in different orders and events happen in different orders, then the results can be different. Yes?
I've personally written a program where it worked 100% of the time in the debugger and 0% of the time when it wasn't.
And that's exactly this word here. I have Heisenbugs. That's the idea, is that the debugger itself can change the timing enough so that exactly that will happen. As long as you're measuring it in some way, it works great. And then once you take the measurement away, it doesn't work again. That's a real problem. So some people have equated non-determinism with bugginess. And I'm saying they're just afraid because the languages and approaches that they've used haven't allowed them to rein in the non-determinism or use it productively. There's lots of cases where non-determinism is very useful. So, so in lots of cases, you don't care the order that the output is produced. You just want it to be produced. In grad school, there was a case where the program was producing a different answer than the guy who gave us the program wanted it to after we parallelized it. And we were trying like crazy to figure out what went wrong. And we finally went back to him and he says, oh yeah, that's another answer. That's another good answer. It just went to another local minimum in a search space, and that was just as good as the answer that it was originally giving when it was running in sequentially. So non-determinism is okay if you harness it correctly. Another approach that is being used is functional languages and special languages, etc. Haskell, whatever. So those don't say specifically what order you want things to be evaluated in. They just say what you want to be evaluated. Of course, there's some restrictions on the evaluation order, of course, and there will be here. But they have some drawbacks too, and I'm not going to fight with the Haskell crowd right now. But sometimes you want non-determinism, like I just said. Mutable memory is there in all computers. It's really nice to make use of it. I guess Haskell has things like monads and things that allow you to make use of some of that stuff, but I might claim that it's unnatural. So let's go into the ScalPL approach. There's two kinds of plans or programs in ScalPL. The basic kinds are called tactics, and the non-basic kinds are called strategies. Tactics are the basic. They're actually built from traditional programming languages, any sequential programming language that you like, nice deterministic sequential programming languages. Strategies are the next level up. They are the composite. So if you think of a plan, a big plan is a tree made up of smaller plans. All of the nodes, other than the leaves, are going to be strategies, and the leaves are going to be tactics. And the tactics are all written in languages like you're all familiar with. I don't know about M4. Speaking of M4, This was implemented in M4 back in about 87 or 88, I think it was. I implemented some of this, and I can, and it worked really well. So all ScalPL plans have an interface and an implementation. That's nothing really amazing. The interfaces look the same whether it's a tactic or a strategy plan, but the body, the implementation looks very different. When a plan is activated, it becomes an activity. That's just to avoid using terms like threads and processes and stuff because these kind of have some different characteristics, so I'll just call them activities. A plan interface consists of roles, and you can think of them as arguments, that they're very similar. Each role has a name, a content domain, which is basically a data type, a usage, which is, you might be familiar with in, out, or read, write, or whatever. They're called observe, replace, and update here, but they're basically like that. A dimensionality, which is fine, just none. So, as we will see, a role does more than just access data, and we'll get to why we might want none in a minute. In fact, we'll get to it just right about now. Another thing that each role has is a transition domain, which is a set of transitions. And that's like a set of signals or exceptions or something like that. Basically, so every single argument or role to your plan has a set of signals or exceptions that you basically describe the conditions under which you're returning that. So we'll get to that in a second here. Yeah, so that's, it can be an array, basically, and we'll get to arrays later on, but it's just basically the number of dimensions in the array. Okay, and plan interface is often illustrated in a graphical form, which just shows the name of the plan as a circle, and then the names of each one of the roles, and then a line representing by the arrowheads whether it's an observe or a replace or an update that is in, out, or in, out. In parens here, we have the list of the list of transitions for each role. So take for that, done with that, more or no more for that, and then the type. Okay, now for the implementations of these plans. For a tactic, the implementation, it's like a pure procedure in Fortran 95. How many people know Fortran 95? Okay, a few. Pure procedure is just basically saying it doesn't have any side effects, it doesn't have any persistent state, it's just doing what it does based on what's in its arguments. It gets the data from its arguments, it produces the results to its arguments, and so it's kind of a real live function-like thing.
Referentially transparent.
Yes. So it's different from a function in the sense that it can get its inputs and produce its results to the same place. So it can like update things in place in a sense. But other than that, it's like a function. So I'll get to that in a second. So all interaction is through its roles, and it can only do the right things with its roles. It can observe the input ones and change the output ones, etc. This is the place where these tactics are different than normal old subroutines or functions. Instead of just returning at the end and having just returning the arguments to whoever called it, we're going to find out that there is no whoever called it. Instead, what it does is it returns its arguments, essentially, its roles, one at a time by issuing transitions to the roles. So every time it gets done with one of its arguments or roles, it issues a transition to it. And that transition has to be one of the transitions that you declared for that role. And it will basically tell the outside world something about that thing that you're returning. It will say, okay, now it's in this new kind of state or phase. And if there's something wrong, I mean, it could actually be an exception like overflow or something like that, if that's what you've declared there. And it'll be up to the outside world to decide how to handle that transition. And I'll cover that in a second about how it's going to cover those. Yes?
I may have misheard you. Have you said these were executed atomically?
So I haven't said that yet, but they are. Okay.
I'm out of sequence.
That's fine.
So I'm trying to reconcile in my mind the executed atomically and the issues are done in some sequence.
The what?
You issue to the things. Could you issue and then have some delay and then another issue to another role that they might know each other by another channel?
Okay.
Or
I'm not sure I exactly understand. So the order, okay, once you issue something to a role, you can't, that role is off limits now. You can't access it any longer. The order in which you issue things to the roles has no bearing on the logic of the overall execution. So the only important aspect of each of these tactics is going to be the mapping or the function that it expresses, and that's what I'm going to get to here in a second. Okay, by the way, so you can issue these roles one at a time. Suppose you issue all the roles and you still have more statements. Well, it's over. I mean, you've already gotten rid of all of your roles, and that's the only way you can impact the world around you, so that's essentially the end of that execution, of that activity. And if you suppose you don't issue all the roles and you hit an end or a return, well, that issues a default transition to all the remaining roles. Yes?
Maybe this is sort of what you were asking too, is are all of the issues dispatched atomically?
No.
Or is it a transaction?
No, the issues are dispatched as they're executed. The thing starts atomically. The thing does not start until it has access to all of its things. And the book goes into how this can all work in a very effective way. It's when people think of atomic transactions, they often think of, holding on to, or two-phase locking and all this kind of stuff, and not committing until the end and all that kind of stuff. It turns out there's a completely different way of doing it, and that is if you don't allow things to start until everything's ready and you atomically get access to everything at the beginning, then you can give them up and it has the same kinds of properties.
It's more of a safer barrier than a transaction.
I'm not sure. I should probably talk to you about that. Okay, so an activity from a tactic, because it has all these special properties, we give tactics activities a special name called an act-on. And they're basically like a function. It's a function from the initial value of all of its observe roles to the final values of all the update roles and the transition issued to each one of its roles. And that is a function. Okay, so we call those act-ons. The activity for a tactic is called an act-on. Okay, so now we've covered tactics and their implementations. Now we'll go on to strategies. Remember, we said these are the complex things built of other things. This is the part that ScalPL is all about. It's the graphical part. So a strategy is composed of resources and contexts. Resources are rectangular things. They're like variables. And contexts are circular things. They're like, just a second here. Okay. Okay, so they're like the verbs. You've got your nouns, which are your variables that hold on to things statically, and your things. So context is where an activity occurs. So a circle is where an activity occurs. And to show which ones are related, you use lines to connect them, and the lines are called role bindings, and that's because they bind the roles of the plan that's going to activate in that context to the resources or variables. So now you start getting a feel for how information or data or content can move through the strategy just by looking at the arrowheads and how that stuff goes. Now, this particular strategy that I'm building, in the book, like I said, it applies this to all kinds of things. This particular strategy is for making and serving waffles and having people eat waffles. I figured it was a good example of something that where all kinds of things can be happening at once. And in this case, you can mix the waffle batter, you can preheat the waffler, you can set the table, you can spoon the stuff into the waffler, you can have two people eating the waffles and getting hungry and asking for more waffles and all that stuff. And that's what this is illustrating. I think as programmers, you could probably see how this could be generalized into more like stuff that's important to you. But and we'll assume that each.
Waffles are important to us.
There you go. I had them this morning just to prepare for this talk.
Should bring some.
I didn't bring any, no. I figured there'd be so much pizza here. So,
We did waffles yesterday morning.
so we can get a feel for how kind of data or content is moving through this, but we still don't have a feel for when things happen and circumstances under which they happen. So let's look at that. So here's a resource. A resource, in addition to having content, like a variable has, it has a control state. So a content state, control state. Control state is a set of states that you just name. And each one has a name. And you can think of states in a finite state machine. So each one of the resources has a little finite state machine associated with it. You give the names of the states. In this case, we've got one named empty, one named valid, done question mark, done exclamation point. And each state, we give either a color or some kind of a symbol just to help us abbreviate some of this stuff that I'm going to talk about in a second. So this kind of says the kind of phases that this variable or resource will go through during its lifetime. And in our waffles case, like the waffler might be cold, and in that case, that's when somebody will have to heat it, or it'll be hot and empty, so that's when batter can go in it, etc. So these states are going to have something to do with who can access it at the time, what can happen, etc. Okay, so each context, when it's bound to these resources, I already showed you these role bindings that connect each context to the resources, there's an access dot, and that tells what control state the resource must have in order for that activity to access the resource. So in this case, plan X here, when it gets activated, can only access the resource if it's green. And Y can only access it if it's blue, that is valid. And Z can only access it if it's purple, that is done question mark. You can actually have multiple access dots. So you can have multiple cases under which you can access. In addition to those, we have transition bindings. And what these say is that when this activity issues this transition name, that it will change it to this the color of the control state. So X, when it issues an init, will change this resource to valid, because valid is the blue control state, etc. So we can kind of illustrate that. So all of them start in an initial control state, and green is the default. And so in this case, X could access it. When X issues an init transition, it changes to blue, which allows Y to access it. Now Z can access it. Depending on whether it issues a cont transition or a finish transition, it will change the control state of the resource to the proper color. And so as I mentioned before, each of these control states of the resource can be thought of as states in a finite state machine. And so you can actually draw a little finite state machine that shows those states. You can consider each one of these transitions in the finite state machine. And if you wanted to finish labeling it, now you've got a finite state machine that describes, for that resource, all the kinds of accesses that can happen and the situations under which. Okay. So one of the nice things about that is that you can focus independently on each resource and see the kinds of transitions that it can go through without necessarily considering what's happening in lots of other places. Okay. So you were asking if it can execute atomically, and the answer is tactics do execute atomically in some definition of the word atomic. That is, they will only execute if they have access to all of their resources. Upon executing, they get access to all of their resources. And that's generally shown by stealing the control state away from all of the resources. And then upon issuing a transition, it grants the control state back to the resource so that other entities can access it. So all of these common things, these common problems that can occur in parallel processing, where the processes have an internal persistent state or internal non-determinism or complex I/O behavior or non-atomic access or deadlock and live lock, all that stuff, we just say, no, we're not going to allow that at the tactic level, and we define it away. Yes?
I'm not sure how in a complex network you could at least manually validate that it doesn't have states that it could get into and not out of.
That it could.
So what you've got is a bunch of coupled finite state machines, right? And do you have tools to validate that it can transition out of all the global states that it can get into?
So when you're talking about global combinations of states, of course you can end up with some of these problems. You can end up with live lock and deadlock and all that stuff. So far we're just talking about the tactic level. Each tactic is not going to, tactics competing with each other are not going to have this. Okay. So, so let's get back to the presentation here. I've already presented all this stuff. I showed you the color representation of control states. When I wrote the book, I had to come up with other notation because it turned out color printing was bad. So there are also black and white representations of this stuff where you just use patterned dots. And the tools that I have, sometimes you don't need to see the names of everything. You just need to see that there are these three states and it can go between those things. So the tools allow you to make the labels go away or show them depending on whether you want those or not. So, there's the waffle thing with all the things. And now, it's only going to mix the stuff into the batter bowl if the batter bowl's empty, and it's only going to, put the batter into the waffle iron if the waffle iron is hot and empty, and it's only going to make more batter if there's people asking for waffles and all that kind of stuff. Oh, and we can actually watch it do some of that. Now, I didn't show the other video, but I don't know if I'm going to have time. But maybe I... Okay, well, actually, let me go back and show something real quick. And it has to do with sequential programming. Another way of thinking about back here. There it is. So when I talk about structured programming, here's a very simple sequential program, binary search. It only works under very, power of 2, -1, number of elements. It's very restricted. But I just want to get a feel for, what you're trying to do here is take all of the possible executions that you'd want to have happen for a binary search and kind of fold them all up. That's what an algorithm is kind of a compacting of all the possible computations you'd want it to produce and folding them all up. And you can think of computations unwinding from this like a piece of string as it's using one particular set of inputs. So, for example, as it's looking for, item 15 here, this is what it's doing. It's following these statements and unwinding this particular computation off of this algorithm. And that's what algorithms are all about. It's like a compacting of all the possible computations that you might want to execute. What structured programming does for you here is it helps you to see what kinds of things might end up close together in the execution, in the computation, by looking at the structure of the algorithm. That is, if things are close together in the algorithm, either physically close or close at the same level of indentation, those are the kinds of things that might end up close in the computation. So that's kind of what I'm taking as my definition of structured programming. That is, the structure of the algorithm itself gives you a good feel for what kinds of things might end up related in the computation. It's also interesting that you can actually see this as a multiple step process. You can see the algorithm. We all think of you execute an algorithm, you get an output. Well, you can think of you execute an algorithm, you get a computation, and you evaluate the computation, and you get the output. You could consider that as kind of a two-step process. And in fact, with modern microprocessors and stuff, they try to see as far in advance what the next statements that are going to execute are going to be so that they can be fetching stuff from faraway memory to compensate for latency and stuff like that. So this is not that foreign of a concept. And then, so the computation can be seen as kind of a function in itself that takes the same inputs and produces an output, but it'll only work on the same inputs that produced it in the first place. Once the control statements have been executed, those really aren't doing anything in this computation anymore. So, but after that, it can just be seen as a function. And it can be executed just like the algorithm was, and it can be simplified to an actual function. And so we can actually think of this as a two-step process where you take the algorithm, you give input, it produces a computation, you take the computation, you give it the same input, it produces the output. That's just some background for what I'm going to present now. In the parallel world, it's like, can the parallel world be seen the same way? And the answer is yes.
Is that meant to be like a declarative type of thing, like splitting apart control and action?
So it's basically it's taking all the control. It's executing all the control first, and so it's basically changing it from a partial recursive function into a partial function. Non-recursive, and then it's evaluating that non-recursive function. Okay. So now here's our waffle example. We start out with all the control states being green, their initial control state. We can see under that circumstance that mix could go and preheat could go and set the table could go, and people could be making requests under those circumstances. And if mix was to activate, then it gets control of all of its resources, and so they all turn black to represent it has no control state right now. And then as it issues transitions to each one of them, it's giving the control state back to them. And once it gives the control state to the batter, that is, it has placed the batter into the bowl, then now spoon can go, and etc. So you can just kind of see how the different pieces, and each piece you can think of, you can just focus in on that piece. You see the conditions under which that piece can go, and you can see from the state machines of each resource the conditions under which each of its neighbors can go. So you don't have to think about everything happening at once. Everything is only affected by and can only affect those things in its immediate neighborhood. So I'm just going to let this go, and now everything's going, and you're saying, oh my goodness, how can I keep track of all that? Well, you don't have to. You only have to keep track of each independent thing. So I'm just going to take that and reorganize it. It's still the same program, and I'm just going to put it off to the side here. And now I'm going to execute it again, only this time I'm going to run a piece of paper behind it and record how everything's going. And now I'm coming up with a computation. And this is, remember I made the computation or the trace along the side of the other one. Well, this is analogous to that. And so how analogous is it? Well, first of all, if you'll remember, the first thing we did is we said we could just execute the computation and come up with the same thing. And this is the same kind of way where we could think of this cursor going along and executing this and saying which things happen next, and it gives the same result, of course. We also said that to actually simplify that, we took out the control statements, all the while statements and ifs. And here we take out all of the lines that relate to, oh, well, I'll get to that in a second. First, I'm going to show that this computation really does look like an unfolding of the program, just like before. We pulled this piece of string off before, and here, so here's a part from the computation, and here's the part of the program that created that. And as you can see, it's really just that thing unfolded. And you could actually, that computation that I showed off to the left there, which I'll show again here in a second, you could actually visualize that as, I mean, I've thought about doing this, I haven't done it yet, but you could actually build the program out of cardboard and string and actually just lift a computation off of that, and it would look just like this. So it really is the program unfolding into the computation.
It looks kind of like a punch card.
Yeah, sort of, yeah.
I thought it was music.
Right, well, it's funny because music has come up many times in this. You know, people see it and they say it looks like music. Also, by the way, people look at a lot of this and they say it looks like hardware when I'm showing the diagrams and stuff. And, but the music thing, the thing about music is it defines exactly what things have to happen at the same time and all that. So it's different from music in that way, but it's interesting.
The computation might unfold in different ways depending on the timing.
That's right. So that's a good point here, is that there is non-determinism in this example. I mean, different computations could unfold from this one program. However, once the computation has unfolded, the computation is a function, and I'm going to show that here in a second.
So it's like music played by a high school band.
There you go. That's right. You give each person their script, and then you say, just play that anytime you want. So before we took out the control statement, so here we'll take out all of the things that just have to do with, you know, control state, that don't have any data state moving around. And then we'll kind of smooth out the lines so that they're kind of simplified. That's like when we simplified the expression. And now this thing represents a function. So if we wanted to see what, how we got this particular result, that is what's left in the batter bowl, we can go trace backward, look at all the things that fed into it, and in this particular case, what happened is we evaluated mix, and remember this is a tactic, it's a function, it's evaluating something on the flour, eggs, and milk, the original flour, eggs, and milk, and then we spooned that out once, that was another function, spooned it out again, so the batter bowl is that evaluation on the original inputs. And this execution defines that, so it defines every node in this computation as the result of a function. So anyway, that's kind of, you know, if you're thinking about formality and stuff, it seems to have some nice properties in that way.
The question is, if it can unfold into two different functions, are those functions equivalent?
Not necessarily. And the book goes into some tricks you can use to show that, you know, under these circumstances, the functions will be equivalent. And in parallel processors these days, for example, reductions, computational reductions of where you're like taking a summation of a large number of numbers, you don't really care the order in which they're added as long as it meets requirements of what do they call, numerical analysis and stuff like that. Make sure you're not losing things in round-off error and stuff like that, because different orders can result in different round-off errors. So you got to take all that stuff into account. So there, but many operations are associative or distributed, so you can use that to prove that it's giving the same results, etc. Okay, another aspect, when we talked about the atomicity of these tactics, I said a tactic isn't going to execute until all of its resources are ready, and then it's going to grab access to all of them, exclusive access, and then it's going to give it up one by one. What does that mean when you've got multiple activities wishing to just read from a single resource? Are they going to block each other out? That would not be a good thing. You'd like them to at least be able to all read the resource at the same time if they're not going to affect each other. And it turns out that with a stroke of a pen, in the formal definition of this stuff, you can say that in certain circumstances, that is, if it's just reading the resource and it knows what transition it's going to issue to the resource, it's only going to access that resource for a finite time, and in formal language that means it could be an infinitely small amount of time, and what that really means is that you can have multiple things in reality accessing the resource at the same time, but it's modeled as sequential accesses to the resource in the formal world. So it turns out that one tiny little simplification in the formal, or tiny little definition of the formal model, makes it so that multiple readers works, readers-writers works where it blocks writers, or makes a copy, and it's all up in the air as far as how the implementation wants to handle it. It even handles double buffering and stuff. All that stuff is described with the same formal description. So it really allows a lot of leeway to the implementation, even though it's all using the same formal description. Okay, finishing up the strategies. I defined what the body of a strategy looked like. I didn't describe how the body and the interface work together. Remember, the interface consists of a number of roles. How do those interact with what's going on inside the body? And the answer is, if we consider this little thing on the right a strategy, there's a special kind of a role called a special kind of a resource called a formal resource, which is shown with a little triangle here, and that represents a role. So this particular strategy has two roles, one named furniture, one named color, and those, when this strategy, which is called repaint, is put into another strategy, which is put into a context in another strategy, well, look at that. It has two roles, and one is bound to furniture and one is bound to color here. And so the content state of this actual resource is basically equivalence to the content state of this formal resource, and same with color and color when that's activated. Now, what about the control state? Well, that's a little bit trickier. And what happens there is that these formals do not have any control state starting off. But once this resource gets a control state that matches the access dot here, then suddenly this guy magically gets his initial control state. So suddenly the innards of of this strategy can now start accessing this resource. And if they do, it effectively steals the control state away from here, brings it over here. Then it can bounce around in the formal resource until it changes the control state to something symbolized in this box, at which point it turns into a transition and goes back here. Yes?
When the formal resource does the formal resource maintain control state from the external resource while it's waiting for all of its...
No.
So,
well,
let's say you're waiting on repaint, but there's a bunch of other stuff that are also trying to do some furniture. Yeah.
Okay.
So repaint's, is it going to block on that?
Okay, so it's only tactics that wait for all their resources to get done, that wait for all their resources to be ready before they activate. You can make a strategy so that it does the same thing. So, for example, in this case, this strategy over here does not have to wait for both the furniture and color to be ready before it activates by default. You can make it so that it has to wait, and the book describes that more, and I'm not going to go into it today because but but generally speaking, so strategies are a lot more flexible. They're a lot more basic. The idea here is, even though I put all these restrictions on tactics about the situations and how they're not subject to all of these problems, strategies are open to all of those things. But there's a number of tools to be able to analyze them and see what things they're actually subject to. So you can make a strategy atomic if you want. You can make it wait until all of the resources are ready. There are some tricks to do that, and the book goes into those.
So, is there any way of rewiring things at runtime? These strategies, can these errors move around and create new boxes?
Okay, so we're going to get to that in a second. And we'll get to that when we talk about objects. Okay, so that's the main part of software cabling. Now I'm briefly going to talk about arrays and objects, and hopefully I'll be done in like 5 or 10 minutes. Okay. Arrays. An array in software cabling, in ScalPL, I'm sorry, I'm still calling it software cabling, is just a resource with some hash marks on the edge. This is a one-dimensional, two-dimensional, three-dimensional array. An array consists of infinitely many elements, and each element is a resource in itself. That is, it has a control state, it has a content state. And I'll say in a few minutes why it has an infinite, well, maybe I won't. It has an infinite number of elements. The reason that's even practical is because of the control state. That is, all of the elements that haven't been accessed yet are going to have all of the default control states and the initial control states and content states. And so you don't have to keep track of them. You only have to keep track of the ones that have changed. By default, when you bind to an array, you bind to all infinite elements. And there are only a few things you can do under those circumstances. But another kind of binding is called a bind any. If you put a question mark before the role name, then it will just pick one element of that array that has the proper control state and bind to that. Now, why would you ever want to do that? Well, let's say you want to allocate stuff dynamically. This is just a very simple way of doing it. You have a one-dimensional array which has infinitely many elements, and you need another resource like that. Well, you just do a bind any to one, and you get it. And then you change the control state so that the next bind any isn't going to find that one. So this is a way of dynamically allocating elements, but that's certainly not all arrays are used for.
Are these arrays literally arrays like sequential?
No. So there's no memory layout specified by the arrays. Each element is an independently. So really the only thing arrays are about is indexing the elements. It has nothing to do with memory layout.
Yeah, but you get constant time indexing. You get constant time indexing.
So, no.
Okay.
The one of the issues here is that in many cases, these array elements are on completely different processors. You know, there are conditions under which it can optimize the indexing, and hopefully many conditions under which it can optimize indexing. But in the general case, it could not guarantee that. Okay, how are arrays elements indexed? Well, these are binding modifiers, and this looks very complicated. Let me first say that only the left side of each one of these subdiagrams is an example of ScalPL. The right side is supposed to be an illustration of what the left side means somehow. So in here, number A, if you just simply bind a context to an array resource, it just, by default, if the activity in there issues an index to AB, it's going to use A for the first index and B to the second, dimension. You can also, as shown in B here, you can put a permutation, so it basically changes the order in which it interprets the indices to index the array. For C down here, this is called a reduction, and it's basically saying you can say get a certain one of the indices out of another resource. So in this case, it's saying take this resource, content state, and use it to index the first dimension of this array. So the the activity inside this context is only going to be indexing the second dimension of that array. And it's only going to see a one-dimensional array.
In that, it looks like you're doing zero-based, but in the permutation one, it looks like you're doing one-based.
So there's
Or just ignore that.
the dimensions are one-based, 1, 2, 3. As far as the indices in each array, since they go from infinite negative to infinite positive, they're any base you want.
Okay.
Okay.
Do they have to be numeric?
Yes, they're just integers.
You base 36 numbers? No.
D shows an example where you can also take out of a resource, you can take a number to add to a certain index. So it essentially shifts the array in that dimension, that amount of space relative to the activity that's accessing the array. And here E is an example where it actually does a translation. That is that the activity issues an access to this array, but what really happens is its indices are intercepted to index this array, and it gets the indices out of that to index that array. So there's indirection there. And based just on these, you can do all kinds of weird things. Now, the first question people are wondering is, why are you doing all these arcane things to do indexing? Why don't you just use simple indexing? And the answer is, again, to attain the things that we want to attain, which is lack of deadlock, which is the ability to tell what elements an activity is going to access before it actually accesses them to compensate for latency. That is, to make sure that the proper elements are in the proper place at the proper time before the activity starts executing. Here's a simple example. This is a bounded buffer problem or a queue. This is the records in the queue. This is the input pointer to the next thing to go in. This is the output pointer for the next thing to come out. As you can see, it's copying the input record into the queue at the point specified by the input pointer. This is saying the first index, which is the only index, the only dimension, is specified by the input pointer. So this just does a copy from the rec in to the buffer, and this just copies out from where the output pointer is pointing. So what is all this other stuff? Well, the other stuff is these increment and test tactics, and they do a very simple thing. They compare two numbers, and if they're equal, it issues an equal transition. And if they're not equal, it doesn't. It issues a not equal. So what is it doing? Well, after you put a new record in here, it increments the input pointer, and then it compares it to the output pointer. And if they're equal, it issues an equal transition, which changes the thing to full, because it has just put in the last record to make the pointers now equal, and now that it's in the full state, rec in cannot execute. I mean, no more rec ins can be copied in because of this control state. So when the buffer's full, it can't copy any more in, and the same thing happens on the other side. When the buffer's empty, no more can be copied out. So that's all handled by those. One more thing for arrays that's very useful with arrays is duplication or context replication. If you put an asterisk next to a role binding, it basically replicates that context that many times. This 4 up here is actually shorthand for a resource containing the initial value 4. So this, once it activates, it actually creates 4 different contexts, each one getting a different value from that resource. And you can see that it could use these different values to actually index into an array. I'm not doing that on this example, but if this thing down here was an array, and these were used as these reductions like I showed on the last slide, each one of these contexts would be bound to a different element of that array and could all be working in parallel. And here's an example of a dot product where exactly that is happening. That is, you've got your one input array, another input array, and these two replications. Here's the arrays expanded out. Now this is going to replicate or dupe all 3 times times 2 times. And if we zero in on one of those, this is saying this is going to see a 3 and a 2 on the dupe all rolls. And this is going to tell which dimensions to fill those into. So this particular context is going to access row 3 of this, column 2 of this, and element 3.2 of this, which is exactly what you want to have happen, is for each one of these, I should be making this bigger, to have each one of those accessing one row, one column, and updating the appropriate element of the output array. So that's kind of an example of where a dupe all might be used. Okay, I'm going to go real quick here through objects. Once I can figure out how to make this work. Oh, by the way, this is a quick sort. I'd love to describe it to you, but it's a very parallel quick sort. It's very interesting because unlike other quick sorts where you first decide all the elements that are less than the pivot and then those that are greater than the pivot, and then you recursively call the two sides, this does it all in parallel. This kind of picks the pivot, and as soon as it has 2 elements over here, it's already calling the next level of recursion to work on those on that side. And so what you end up is an entire decision tree of elements working concurrently with all the new elements kind of tumbling in the top and siphoning down to where they need to siphon to.
So doesn't that become a bin sort? Or
Yeah, it starts looking like anything.
It's not a quicksort anymore.
That's right, exactly. You make it parallel and suddenly it's not a quicksort anymore. I thought that was interesting in itself. Okay, classes. I'm going to just go through this really quickly. So what's missing? We have these strategies. They have well-defined interfaces. We can almost think of them like objects or instances or classes or something. But why can't we? Well, first of all, we need them to be first class. We need them to have persistent internal state. That's what it's all about, is data hiding, information hiding, encapsulation. Have to have some form of inheritance. Have to have partial binding. That is, we have to be able to activate just certain methods inside. So the first step is, I told you before that a context was labeled with the plan that goes into the context. Actually, that's a syntactic sugar. That really means it takes the plan, puts it on a resource, and feeds it into the context with a special role named $plan. So what these contexts really do is they look at their $plan resource, that role, they find a plan there, and they activate that plan. So you can have plans moving around. You can update which plans any particular context is going to activate from time to time.
Is plan like your list planner? C++.
Is it, I didn't get
Like your list pointer, there's a list pointer, or something like it's my pointer, points to yourself. Self.
Well, it's not. He's wondering if plan is like this, a self pointer, and I don't think I'd describe it that way. Plan is just an argument. In essence, it's well.
is it main?
No.
Does it sound like a
$plan, it's just simply a role that's bound, or an argument if you want, and it just says what to activate. It reads the description of the plan that it's supposed to activate from $plan, and it activates that. I don't know that I consider it a pointer exactly.
Well, I think that's your pointer. In some object languages, you want to refer to yourself, so you say this.
Oh, there are ways to refer to yourself, and that's not it. But I could get to that if there's time.
I was just wondering if plan is bound to a process. At some point it's set to execute an environment, right? So
Right, so that's exactly, this is the environment. The context is, in a sense, the environment that it's executing within. So the context looks at what's to execute in this environment. It binds the roles of whatever's to execute there, and it executes or activates it. So that's, in essence, what the context is all about, is to bind and execute the plan.
But it binds to can change based on data.
Well, the bindings, the role bindings are as I described. That is, they're generally static. There are ways to index, through arrays and stuff you can change their indexing. But what you want to know what the bindings are before activating the thing, because that allows you to compensate for the latency in the system. You like to get the data to where it's needed before it's needed there. Okay, next. As far as persistent internal state, I've shown you contexts that are just one circle and resources that are just a rectangle. You can have instantiation levels of resources and instantiation levels of contexts. What does that mean? A context, when it starts up a strategy, it has to instantiate all the resources in that strategy. It has to create them. It has to initialize their content state and their control state, etc. And then once that strategy is done, those things can go away. And strategies can finish and restart, and that's kind of stuff I haven't really described that part. What these different instantiation levels do is they say, okay, only instantiate the resources that are at the same instantiation level as the context. So the instantiation level is the number of shadows. So this is instantiation level 1, 2, and 3 for the context, 1, 2, and 3 for the resources. So this says only instantiate resources that have 1 shadow, only instantiate resources with 2 shadows, only instantiate resources with 3 shadows.
Is this like a recursion stack?
It's not recursion stack. I'll give an example here on the next slide, which I hope will illustrate what some of this is used for. In addition, contexts with instantiation level greater than 1, or greater than 0 also have a $O plan, which says write out this strategy, write a new copy of this strategy out that has these resources instantiated. Okay, let me see if I can describe what we're talking about here. On the right, we have a strategy. It has 2 roles, X and Y. It has 2 resources internally, F at instantiation level 0 and G at instantiation level 1. Here we take that strategy, and here we put it into this context and instantiate. It's at instantiation level 1, so it will instantiate G and write the resulting strategy out to here. And now G, the resource G, is now instantiated. We can now feed that as the input to these 2 contexts. Remember the $, plan? We can feed things into these different contexts. So now at these, it's going to instantiate just the instantiation level 0 stuff, which is F. So what does that mean? It means that this is going to have a level, this is going to have a version of G instantiated. This is going to have a different version of G instantiated. And both of these are going to use the same version of G that was instantiated over here. And both of these are going to use the same version of G that was instantiated over here. In other words, this is acting like a class. This is acting like creating an instance of that class. That is, we've instantiated, we've given each of these instances its instance variables, and in this case G, and this its own version of G, and then these are basically calls to the class. Yes?
So, can you partially instantiate something based on the number of levels?
You can definitely
G
partially.
was at level 2, and I only called it to level 1.
Yeah. Yeah, so you can control these any way you want. Generally, you instantiate from the higher levels to the lower levels in various steps, and by that you can make meta classes, etc. So different classes sharing certain variables, different meta classes sharing certain
So-
state.
Is F then like a class level
So-
shared amongst all the instances, or?
So F won't be shared by anyone. F is instantiated separately in each one of these different things. So F is just like a local
Okay.
variable that's used at each procedure call or each method call. So G is the instance. G is the instance variable here. So that's how it handles the persistent internal state. You basically instantiate whichever parts of the state you want to, and then it's encapsulated. There are some ways that this doesn't look at all like a class, and that is, for example, each time I use the instances, I have to bind all of the roles, and so it's not like I'm calling a method. I'm kind of calling all the methods at one time, and maybe I don't want to do that. So that's another aspect is partial bindings. You can declare that you only have to bind certain things at one time. You can put an expression of exactly which things have to be bounded at any one time. And the last thing was some form of inheritance or delegation. And that's handled in kind of a weird way. And this is the last slide, or the last concept. Basically, you can group together these formal resources into sets of formal resources, and you can bind them using role sets, they're called. And so you can actually carry sets of resources into and out of these contexts. And in fact, you can represent parts of it using a wildcard, an asterisk. So you can basically say, I'm getting some kind of context from my surroundings ported into me. Remember, this is part of the interface of this strategy. So something outside is defined what this is bound to. It's bound to at least these things, but it might be bound to all kinds of other things that I don't care about. So we can put a wildcard there. And I can basically carry context through me, or scope, whatever, through me and into other contexts that I'm carrying. That was probably really confusing, wasn't it? Let's see if I can describe it at all. This is probably going to feel more confusing than it is. And maybe I should give up. Basically, roles, remember roles used to just be bound to a particular resource. Each role was bound to one resource. Now a role can be bound to, this is another symbol which allows you to group these together into a set, which is now called H. These are now pulled into a set called I, etc. So you can group all of these things into a single set, and that set can be thought of kind of like a cable. And that's one reason that this was originally called software cabling, is you can think of this like a multi-level way of bringing the outside, world into you.
It's sort of like a big hash data structure or something.
Actually, it can be almost anything that's a nested structure. It could be a file system. You can bring the outside file system in. You can bring your exceptions out to the world in some sort of a nested form so that the outside world could interpret those. You can consider this all kinds of different ways. So you can, it's part of the interface here. You can think of it as, some sort of a set of pins that's kind of hierarchical. But as far as the interface or inside of the strategy, it's represented something like this. It's represented as a nested set Okay, so that, believe it or not, that is sufficient to give you delegation and effectively inheritance to create object-oriented programs with. So like porting global variables in or out of a context, or exceptions, or file system, or whatever. This is a way of carrying large portions of scope into or out of a context. Okay, so that's it. I'm going to give one more slide that just tries to sum things up a little bit. This is an example of a cell phone where we take an object, cell phone object, or cell phone class, and extend it to do things like speak. You know, if you highlight some words on the screen to allow it to speak and stuff. This might be a diagram of how that would work in different, to an extended class. Okay. Things to think about. This is the end. A lot of this stuff looks like hardware. And like I said, I've been in coffee shops, people have looked at it, they've said, that's hardware. And I say, no, it isn't. People sometimes claim if we could only make software more like hardware, we could apply all these nice things like verification and stuff that we apply to hardware to software. Well, this stuff does look like a lot like hardware. And maybe it will allow things like that to have happen. Concurrency and parallelism, some people complain about the differences between those. I don't. I mean, I've just been treating them as all in the same camp, and the book goes into, you know, differences and or similarities. Is it beneficial to talk about parallel programming in the same way we talk about planning other concurrent tasks? Well, I'm hoping to see that as a result of this book, whether people actually find advantages there. There have been claims that visual programming languages are useless, that there's no way that they could ever be practical. The no silver bullet essay that was written a long time ago went into that, and people always cite that as, see, just give up.
Somebody wrote an article.
That's right, somebody wrote an article, and they were really smart, and we don't know what they're talking about. So, but what I've tried to do here, as I hope you've seen, is to create just a few constructs that can fit together to do things like object-oriented programming if you do it right, and other things. But there's not a huge number of constructs. It's just that if you put them together right and use all the other normal sequential programming for stuff it's really good at, then, you know, maybe they'll work well together.
So how does this work in practice? You draw some diagrams and then you put your tactics in foreground dimension or something else, and there's something that puts it all together? Or?
Yeah. So I actually long ago wrote some software to just, you know, it's just very simple stuff. It's written in X11. I wrote it. I originally implemented this in like 92 actually, in X on a Sun workstation that I just bought when NASA refused to let me implement it there. And then it's still running on my Apple in X11. But yeah, you just basically draw out the diagrams and compile it down. Now, let me say that I do not have full implementations right now of the stuff that I've shown you. I have made implementations of this stuff that have run on Cray processors, on Sequent processors back when those existed, on some various parallel processors. I've made runtime systems that have run on other networks and processors, and those still. Now GPUs, I haven't, but it's obviously the buzzword of the day, and people want to know, how does this help GPUs? And I'll have an answer to that real soon. Yeah.
So I've got 3 questions. I'm going to give you all 3, and you can figure out
Okay.
which one you want to answer. You can ignore the other 2. When you're talking about everything having to be ready simultaneously for it to go atomically, the word simultaneously in a distributed system sets off all sorts of red flags.
That's
for
right.
me. So that's one.
Okay.
It's like relativity, there's no.
Yeah, exactly.
Nobody
Nobody
knows something.
knowing simultaneously. Yeah, and unless you're going to have like some sort of global lock and all the latency that implies. So the
Right.
simultaneously bottom.
Okay.
2, when you're talking about going through and threading and then pulling out of the control things, those control things you were pulling out looked to me like they were dependent on the time-based values of the local variables, like in the binary search, right? What value that variable had at that point in the implementation. If you were to renumber them, it would still depend on those computed values. So that bothered me a little bit. You say, oh, well, you can just pull out the control stuff, because it looks to me like the control stuff is deeply tied to the input values.
Oh,
and the third
yes.
one, I'm really impressed with the transitions on your slides. I was wondering if you used to make your slides. So any one of those three, I'd love an answer.
I'll answer the last one first. A lot of these animations I did years ago in using Flash. I learned how to use Flash stuff, and it turned out that you can link to a file, and if it recognizes that as a Flash file, it'll start it up. So it just happened to work out really well. I just discovered that a couple of days ago.
The shapes and everything?
Oh, the morphing is all within Flash animation.
Wow.
Okay, that part. As far as the control, the results having to do with the control statements and stuff, that was your second question. You're absolutely right. So I think some people get tempted by what I say to think, oh, I can just throw away the algorithm now and just use this computation as the new representation of the algorithm. But that's not true at all. So the computation is just only works for the algorithm evaluated on those specific inputs. So what's essentially happening is the trace is taking care of the control statement part of evaluating the algorithm. And then, well, but that's why you need to feed in the data into the algorithm in order to even to. That's right. Yes. Right.
That's a very
Yeah, you're right. Right. We're not talking about branch prediction and stuff like that here. We're talking about using concrete data to produce the computation. And now this computation is just an example of what works for that specific data set.
So it's like a lazy, it's what's left after a lazy.
I guess you could say something like that. Let's see, the first one, oh yes, let's see, what was it again?
Simultaneity.
Simultaneity, oh yes, okay. So, yes, you're right, and I've heard some people on the internet claim that as, so this is very similar to Petri nets, and I think you were mentioning some time ago that you were looking into some Petri net stuff or something. And some people, Carl, what's Carl's last name? He was making an argument about Petri net models not being real world because of this exact issue. And the point is that there are cases where that is an issue. You can partition the strategy into pieces so that you can have local locking or whatever to determine for those specific parts, the simultaneity issue is a problem. But for quite a lot of the rest of it, there is no competition for the resource. For example, if your entire strategy, there are no two activities bound to the same resource with the same control, same access dot, then you have no problem with competition for resources. You have no locking at all that's required. So it's a trade-off usually between those two extremes.
And you
So-
do that statically.
Yes. So you can do a static analysis on the strategy to decide, and the book defines this thing as rivals and rivalries, and you can just lock within the rivalry, and it'll tell how to do that. Basically, the scheduling is often done just with a counting type arrangement where each context just has a number, which is the number of reasons I cannot activate yet. And every time one of the resources changes control state, that count gets updated, and if a count goes to 0, then that activation occurs. And if there is a case where there's competition, you have to control the access to those counts with a single lock or something, or have it happen.
keep two things from simultaneously.
Well, that's what I'm saying, is that there are only certain cases where you have to control that. They can be determined by static analysis, and then it's a runtime system thing that does that. So when I was mentioning implementing this with M4, that's exactly what the M4 did, was these issue statements in the tactics. Those were M4 macros, and it expanded those into these locking what needed to be locked, decrementing or incrementing the appropriate counts, determining what had to be scheduled, et cetera. All that was happening in line, basically. The scheduler was in line on the tactics at that point.
Is this more for simulating large parallel networks, or for actually like,
I sure hope it's for actually implementing. You could certainly use it for simulation, and
how
my.
does it handle like highly latent nodes?
It's all built, as I mentioned several times, a lot of the features of this are explicitly there to make sure that it knows what data is going to be needed before each activity is actually activated, each plan is actually activated, which allows the data movement to occur before local resource registers and things are actually need to be allocated. So data movement can all happen in a latency tolerant manner behind the scenes while other stuff is getting executed. That's kind of what this is all about, is creating as much parallelism as you can and then allowing all the data movement to occur not embedded within any particular execution but between executions. And the book, again, goes into significant detail about how to make that happen and what a runtime system that I've implemented looks like to actually make that happen on a wide number of processors.
It's scale of system. I mean, you said you run
I-
how much data?
Right. The runtime system I was just actually testing on a few systems using very fast networks. It wasn't really that many systems. It was at NASA. They had a bunch of networks they wanted to test out, and I was using that to test them. A lot of this stuff, I mean, I need help implementing a lot of this stuff and making it as good as I think it could really be for the world. So far, everything has been pretty much me that's done it, and I'm getting older. I could really use some help.
Show of hands, who isn't?
I
I
know.
What a relief.
I'm-
If somebody stuck up their hand, I'd be telling you, let's go.
that would be good. I mean, okay, now it's exportable. You tell me how this works.
Or if somebody wants to steal it, I put all my ideas in the book. They can read the book, steal all the ideas, and then hopefully call me every now and then as a consultant.
Well, thank you very much.
Well,
Thank you. And the book's on sale if you want to buy one. And the book's on sale if you want to buy one. I can sell it to you cheap tonight. What? That's right.
I'd also
Oh,
like
thank
to,
you.
I'd like to thank Pat.
Yes.
Absolutely.
Yeah. I said I'd like to thank you. I've got a pretty high standard for eclectic, and this group is meeting it.
All right.